and so on. So what is true of stochastic processes? So let's look at some examples. If you have an arbitrary stochastic process, the entropy can be all over the place. You have a high entropy event and a low one. Even if they're independent, as long as they're not identically distributed, the entropy can be anything. So you can't say anything in general. Now, if it's a stationary process, it's constant, as I mentioned before, and so I've become interested in the entropy given the state I. So let's see what happens. If I'm here in state I, the entropy of the next step is 1 bit. It's half-half. But now if I'm in state B, the entropy is 0 of the next bit, conditioned on being in state B. So the entropy doesn't go up or down. It's just not necessarily monotonic. The interesting thing is if I look at a stationary Markov, this can be stationary. I just started in a stationary distribution. And then all of a sudden it does become monotonic. That's because I dip in and I may get state A, B, C, D, or E with those mu A, mu B, etc., etc. And when you average all that, it turns out to be monotonic. Yeah, see that process? There's the transition matrix. How the entropy given that you start in state I goes. None of them are monotonic functions. But when I average over x0 according to the stationary distribution, the average of those curves is precisely that one, and that is monotonic. It does increase. Here's another process. With that transition matrix, again, the entropy is all over the place. But if you dip into stationary, and that's why I said pick a number between 10 and 20. I wanted you to dip into the process, the English text process, according to the stationary distribution. So let's see what are some things that we can say. What about the entropy of the present x0, given that I look n years back in n time units back in history, back to the beginning of time? No matter what the stochastic process is, stationary or not, I get an increase. The farther I go back, the more uncertain I am of where I am now. Why? Well, look, the past up through minus n includes x minus n, and then the n plus 1 past. And now I throw that away. Information doesn't hurt. I get this. So in short, yeah, of course. I'd rather know the history up through n years ago than the history up through n plus 1 years ago, because there's more information. So that's always true. Well, is that what I mean by the second law? No, but this is a start. We're building up what we know about processes. Well, here seems like a similar statement. It's the entropy n units in the future given the past up till now. It seems you just slide things and get an increase. Well, for this you need stationarity, so I urge you to take a look at why you need stationarity here. But here's the proof using stationarity. The entropy of this, given the past, is equal to the entropy where I've slid everything to the left by 1 unit of time, and then I throw away one piece of information. So, be sure to look at why is it that you can't state that that's true for stochastic processes, why you need stationarity. Now we want to prove that conditional entropy increases. So, for this, we're not only going to make the process stationary, we're going to require that it be Markov. Okay? So, you get the change in the conditional entropy, being this, it's equal to that. Now I add one term, but because the process is Markov, the conditional distribution given this, given these two, is just given the most recent. And then I change the time scale by adding 1 to each index here. And by stationarity, that stays the same. And lo and behold, I get the mutual information between the process at time 1 and time n, given what it is at time 0. And that's always non-negative. And here it is. So indeed, for stationary Markov, the entropy of xn given x0 is always increasing. So that's the second law type statement. Now here's something that's not in the books, in the text, but if you take a look at the second derivative, we could prove that that is concave. I think that's fun. So the second law says entropy increases. This says it increases less and less fast. The proof of concavity is there in the handouts. But when you're all done, it turns out that the second difference is given at the top. Turns out to be minus the mutual information between x1 and xn minus 1, given x0 and xn. So it has to do with the mutual information, and this is exact. And of course, the mutual information is always non-negative. Good. Now, the time symmetry we proved at the beginning of class that if a process is stationary, then the entropy looking into the future and the entropy looking into the past is exactly the same, conditioned on the present. Now, something more is going on in our universe, and it's probably this. It probably is that our initial conditions are in a low entropy, and what we're doing. Expanded universe and so on. You need something like isotropy, I guess. Each state sees the other states as their same. Just to say all initial states are roughly the same. That is, knowing which state you will not change the way entropy increases given that state. So, if you have a Markov process like that, then the stationary distribution will be uniform, which is maximum entropy, by the way. Now, not only does Xn given capital X naught increase in concave, but now, regardless of your initial state, it will be increasing in concave. And furthermore, it will increase to its limit, which is log m, at least for an irreducible Markov chain that's isotropic. And so you don't need stationarity for the concavity of the second law. There are those who would say that the fact that we have an arrow of time, that entropy increases as time goes on, is due to the fact that we started in a very low entropy state and that we are slowly reaching equilibrium, which is the maximum entropy distribution. And you say, wait a minute, Big Bang. What could be higher entropy than a Big Bang in which we had a quark soup, everything was uniformly distributed, it was very hot, photons couldn't even get through it for 100,000 years. That seems maximum entropy to me. Well, what's happening is that you forgot that the gravity started in a very low entropy state, and it's taking a while for gravity to have its effects. The universe is expanding and so on. And until we're in equilibrium with gravity, we won't be in a maximum entropy state. So we started in a low entropy state because we started with a Big Bang. We didn't start with a stationary universe. By the way, you know, before Hubble found the expanding universe, people strongly thought we were in a steady state universe. That is, we were part of a stationary process. Einstein in the constant that would keep the universe from collapsing. His biggest blunder. All right. Here's an isotropic process starting in a state I. Every sample function looks like that. The entropy increases. We'll take a 1-minute break, and when we come back, we'll look at how entropy, how we can throw away Markov assumptions and get a very strong theorem.
Back to stationarity, so you said it's sufficient, but is it necessary as well for this one?
Yeah. Yeah.